Welcome everyone to the first session of ITC, the first in-person session, though all speakers and also myself are going to be connecting remotely. So I have three really great talks today starting us off in this conference. And the first talk is going to be about the distributed discrete logarithm problem with preprocessing. And Pavel is going to give the talk, and I'm going to delegate over the task of pronouncing all the names of the authors to you, Pavel.
Okay, thanks, Mor. So I'm very happy to be here, at least virtually. And yeah, unfortunately, I couldn't make it in person. So this is joint work with students from Charles University, Ľubica, Jančová, and Veronika, Králová. And what we looked into is the distributed discrete logarithm problem in the preprocessing setting. So here on the first slide, it's Ľubica, and here is Veronika playing chess. So let me review the distributed discrete logarithm problem. It was introduced by Boyle, Gilboa, and Ishai in 2016 in the context of homomorphic secret sharing. So it is an abstraction for the problem of converting multiplicative shares of some secret into additive shares of the secret. So we start with some group elements, and we want to get some integers. And what is the setting here? Well, the parties, Alice and Bob, and also the challenger, they have access to some group, which is generated by some element G. The order of the group is N. And then the challenger basically creates multiplicative sharing of some secret X, right? So what does the challenger do? It picks a random B, right, from Zn, produces a random group element, right? So it's a uniformly random element from the group, sends it to Alice, and Bob gets the matching multiplicative share of X, right? This is G to the B plus X, okay? And now the goal of the two parties, of Alice and Bob, is somewhat unusual. So Alice and Bob may not communicate. They are not allowed to actually talk at all. And they have to produce some integers, U and V, such that U and V are actually additive shares of the secret X, right? So the goal is this. So I just want to say that even though I'm talking remotely, feel free to ask questions. I'll do my best to take a look also at chat, and if there's anything unclear, just please ask me. So, like, clearly, you know, there are some natural strategies that they could take in order to solve this problem. Like the first thing that comes in mind is, well, Alice and Bob could both just solve the discrete logarithm problem, right? They could just, given G to the B and G to the B plus X, they could just compute B and B plus X and output this to as their U and V, right? And they would be done. Like this clearly satisfies the requirement. However, you know, this is not okay, because we want to use the distributed discrete logarithm problem in the setting where discrete logarithm is hard. So they don't have the ability to actually solve the discrete logarithm. They have to do it somehow otherwise. However, their task is easier, right, potentially, than solving the discrete logarithm problem. They just need to output integers U and V that differ by X, right? And this might be easier than solving the discrete logarithm problem in the group. Okay, so this is the thing. Another observation is, well, they could also just guess, right? And the success probability, right, kind of is proportional to the space of the secrets, right? So this problem has a parameter W, right? And this is the size of the space of the secret. So we can think about as the secret X being sampled from the interval minus W over 2, right? And this is exactly the offset of the two group elements with respect to multiplication by G, okay? So, right, they could each guess and succeed with probability, let's say 1 over W squared, right, at least. So what is known about the distributed discrete logarithm problem? Well, there are some protocols solving it, right? Already the first work by Boyle, Gilboa, and Ishai, they gave a protocol that works in arbitrary group. They looked at the DDA setting, but it's not specific to any group. And in order to achieve error probability delta, they gave a protocol that runs in time O of W times log1 over delta, okay? So I'll tell you something more about their protocol. What is important to note here is that, well, we want a good correctness guarantee from the protocol, right? So here, like, somehow the protocol is probabilistic. There is some error probability. So we would want the probability of error to be as small as possible. But here clearly, right, the error probability depends on the time that the parties take, right? And in particular, if I would allow time that is polynomial, then I would pay in terms of error a lot, and I would have inverse polynomial error. So that is an issue. So subsequently, because this distributed discrete logarithm problem is very important in the applications towards homomorphic secret sharing and secure multi-party computation, Dinur, Keller, and Klein came up with a huge refinement of the protocol of Boyle et al. And they actually did a very significant speed up. So they managed to get a quadratic speed up. So in order to get error probability delta, right? So they shaved off the log factor and even managed to get to time, right? So T is here like roughly W over delta, right? Yet, like, the same criticism still applies, right? If I want, polynomial time protocol, then I would pay by inverse polynomial error. So this seemed to have been the end of the story, because Dinur et al., they also gave a matching lower bound. So they showed in the generic group model that actually, like, you have a lower bound on error, which is omega W over T squared, right? So like, I'll be kind of swapping between the bounds on the running time and lower bounds on error. So this is actually bound on error, which matches the bound on the error implied by this protocol. So that is the best thing that we can do generically, right? For distributed D-log. However, last year in crypto, there was a very exciting result by Orlandi, Scholl, and Yakubov. So they showed that in a specific group, if you exploit the structure, and they looked at the Pilier group, you can get a protocol that has like perfect correctness and actually runs in constant time, right? And this is very much due to the structure of the Pilier group. So it's not generic, but it pushed a lot all the applications of DDLog to being very practical. So here is a small star, because if you would want like perfectly correct protocol, then we would need to like sample the secrets from Zn, from like a finite group, not as an integer. If you would want to work over integers, then you have like exponentially small errors, so which is still extremely good for the applications. Let me maybe just say something about the applications. So for the homomorphic secret sharing, you are using this distributed D-log protocols, as I said, as a multiplicative to additive share conversion subroutine. You can imagine that you will use it over and over again, right? So if you have some error, it will propagate throughout and accumulate throughout the whole homomorphic evaluation. And then that's the reason why like significant error is going to cost you a lot in terms of the whole protocol. And in particular, if you would go back to the Boyle et al., they had to work a lot in order to deal with the error of the distributed discrete logarithm protocol that they used. Now, okay, so it should it maybe seems like the story is over, right? We have a great protocol, right? And we should be all happy. But this distributed discrete logarithm problem seems to be an interesting problem to study. And in particular, this year in ITCS, Boyle et al. Gave an interesting application of distributed D-log. They gave locality preserving hash, whatever that is. I'm not going to go into the details. And they actually relied on the generic optimal algorithm of Dinur et al. So here is another application of distributed D-log. And maybe there are others. So I invite you to, after the talk, to think about it. So let's take a look at the distributed D-log bit closer. And so the observation of Boyle et al. Was that it actually can be cast as a kind of a synchronization problem. Okay, so as I said, it might be easier than standard discrete logarithm. And in particular, it seems that it's enough for the parties to agree on some special point in the group. So what do we see on the slide? So this is a coset of the group generated by G. Right, and here are the inputs for Alice and Bob. Right, so Alice got G to the B, and Bob got the input of Alice offset by X. Right, so here I'm taking X multiplications by G, which is at most W. Right, this is the difference of the two inputs, and the protocol of Boyle et al. Is rather straightforward. You can think about it in this way. So let's say that the parties, Alice and Bob, they agree on some special points in this group using a PRF. So they use PRF in order to select some distinct points, these gray points in the group. And given their inputs, they just do the following thing. So they just keep on multiplying from their input by G until they hit the first distinguished point in the group, right? So in this particular example, Alice would just go right all the way here. Bob would also go here, and you can see, right, that now they each took, well, B plus X. So they just took some number of steps, let's call it U and V, right? And we have the property, right, that the number of steps that Alice took, right, minus the number of steps that Bob took is exactly, right, X. So they could just output the number of steps to the distinguished point, right? And it would satisfy the guarantee that we wanted to have from the distributed D-log protocol. Right, and you can see that this definitely depends on the distribution of the points in this group and the number of steps that they take. Right, you would want to avoid some kind of like overshooting. Right, shouldn't be that with big probability the distinguished point would lie somewhere in between. So we need to analyze this carefully. But Boyle et al. Showed that this simple idea gives somewhat robust protocol. And then Dinur et al. They really took this idea to the next level, introduced some very nice random walk, and got the quadratic speedup, right, which is optimal in the generic group model. So this is for the distributed D-log, how it is solved. And now, like, one could ask, right? Well, given that, for example, in the context of homomorphic secret-sharing, we'll keep on solving this problem over and over again with a fixed group, right? So the group is fixed. We will get different inputs for Alice and Bob. Could they use some pre-computed advice in order to amortize the cost of these protocols? Right. So this is like what we consider. So here, we would hope that you can take a look at the group beforehand, right, and output some special distinguished points that actually allow you to go below the lower bound in the generic group model, right? But without pre-processing. So, okay. Now, this brings us to like the information theoretic part of our results. Right? So we analyze this problem in the generic group model with auxiliary input. So there's a line of work started by Corrigan, Gibbs, and Kogan, and then later refined by Evgeny Dodis and his co-authors, among whom was like Xia Guo. So they studied generic group model problems, assumptions with auxiliary input, right? You would like to understand the security of some group theoretic problems against non-uniform adversaries. And we have some very strong trade-offs or lower bounds on the power of preprocessing. And the first thing is that they do apply directly to the distributed D-log, right? Because if you have an algorithm that solves the distributed D-log problem, we actually have an algorithm that solves the standard D-log problem, right? So any lower bound for D-log applies as a lower bound to distributed D-log. However, right, so what is the problem here is that these lower bounds are not very refined. Right. In particular, what I would like to understand, and if you think about the problem for a while, also you would like to understand it, is how does the performance of these algorithms depend on the interval length parameter, right? On the size of the space of the secrets in the distributed D-log problem. And unfortunately, if you would just apply directly the lower bounds for D-log with preprocessing to distributed D-log with preprocessing, you will like omit this dependency, and you know, you will not get as good qualitative bound as you would want. So like this was the starting point of our work. We asked, well, does preprocessing help in solving the distributed D-log, and in particular, what are the qualitative bounds that one can get, right? So let me just give you like the summary of our results. Well, we showed that any generic protocol for the distributed D-log in a group of order n, where the distributed D-log problem is with respect to interval length w, and we have running time t and preprocess advice s, has success probability O of this expression. Okay, so no, I don't have much time, so I will not go into the details of this formula. If you looked in, if you're familiar with trade-offs on like, let's say, D-log, this looks very familiar, and it's exactly like the kind of expression that you would expect. And now I will try to like give you the gist of the result that we got in this setting. So in particular, right, if the interval is somewhat small, right? So if w times log w is smaller than n, then the above expression simplifies significantly, right? And we just get a term that depends on w and t squared, and something that depends only st and the size of the group. Okay, so now let me interpret the results, right? So that you don't have to do it in your head. So I'll start with considering what are the practical parameters that we care about, right, in the setting of distributed D-log in the applications. So, for example, for homomorphic secret sharing, W is like poly in the security parameter K. Okay, so if it is poly in the security parameter, it means that it is polylog in the group size, right? So W is you know, can think about log n. So in particular, right, then we have that n is greater or equal than w times log w, right? Because w itself is polylog n, so log w is like log n, right? So this bound does apply, the simplified bound on the success probability. And let's consider different sizes of advice. Okay, so I'll split it into two cases. The first case is when what I would call small advice, even though it's not like necessarily very small, but we have a bound on the size of the advice, which is n over w. So you know, like I have advice of let's say something smaller than n over log n, right? Then the bound that we got here translates to the trade-off, which is t squared is omega of epsilon w, right? And this is bad news. So why is this bad news? Well, because this is matched by the protocol of Dinur et al. So on the table, a couple of slides back, I had exactly this result by Dinur et al. They gave a protocol that is online only, doesn't use any pre-computed advice, right? The smart random walk protocol, and yet it achieves the trade-off t squared is O of w over 1 minus epsilon, right? Because I mean there I had delta, so delta was the error probability. Here I have the success probability, right? So basically for this small advice, when we have an upper bound on the pre-computed advice n over w, right, we are actually matched by a protocol that doesn't do any pre-computation, right? So here, pre-computing asymptotically doesn't help you at all, right? And okay, so how about the other case when we have big advice, right? So we have advice that is of size n over w, right, omega of that. So then the bound that we have here actually translates to a trade-off that matches standard trade-offs for D-log, right? So this is something that Lior will cover in the next talk, right? So here I'm getting the trade-off as t squared is omega epsilon n, which really like looks like the same as standard trade-off for D-log, and that is again bad news, right? Because with advice of this size, I could in principle just solve the I could just solve the standard D-log. And you know, like I said, I need to solve the distributed D-log without breaking the D-log. And you know, here I'm just allowing too much of the advice. So this is like the gist of the results, right? In both cases, we see that the pre-computation doesn't really help at all, at least for generic algorithms. So just a couple of notes about our techniques. So, well, we built on previous works, right? Clearly. So Unruh and Dodis and their co-authors, so they have this extensive line of works on like non-uniform adversaries, right? And there is this framework of unpredictability applications that you can use, for example, to give lower bounds for preprocessing algorithms for the generic group model. One big difference that we had to address is that, well, in our problem, in the distributed D-log, there are two protocols, two algorithms, right? Alice and Bob. And the problem is hard, right? Because they cannot talk, right? And you would want to capture this in order to get a better bound, in particular a bound that captures the size of the interval W. So we had to adapt the previous works to the setting of distributed attackers and kind of address this technicality. Now, on a like, really technical level, what is the core of these lower bound proofs is that, well, there is a so-called bit fixing model, which is a very nice abstraction where it's easy to prove lower bounds, but it doesn't really correspond to the auxiliary input model. So you need to like translate a lower bound in the bit fixing model to the auxiliary input model. And this is like some non-trivial proving to do, right? And there's usually some loss in the proof. So fortunately for us, if you just take the proof of Coretti, Dodis, and Guo from 2018, then this type of statement follows also for distributed attackers, and you know, that is okay. One important thing that we had to address is that most of the previous works on the discrete logarithm problem like considered the generic group model where the generic group doesn't allow you to submit inverse queries. So, right, like in a group, you can compute the group operation, you can right, get the representation of the unit, right, in the group. And you could in principle ask for a group element to get its multiplicative inverse, right? Or, given the group operation, you could implement it yourself in like log n group operations. But for us, this we cannot allow that, because if we would implement the inverse queries via just the group operation and introduce this overhead, then for many settings of the length parameter w, we would get meaningless bounds. So we had to actually consider the variant of this model where we handle the inverse queries explicitly, but it's a technicality that can be handled, and it was fine. So in order to conclude, right, there's a negative result. Preprocessing asymptotically doesn't help in the distributed discrete logarithm problem in the generic group model. One thing that seems interesting is there are these distributed attackers. So is it something that is more general, like it goes beyond the context of the distributed discrete logarithm? And given that I'm not there in person, like we don't have the chance to interact, but I would be happy to schedule a Zoom call if you have any questions. So feel free to send me an email, and the full version of the paper is on ePrint. So thank you.